Hi friends, welcome back to our YouTube channel. Today we have to discuss about floating point representation in computer organization course, computer architecture course, digital logic design course, switching theory and logic design course. In this video, we are discussing about some points. What are the types of numbers? What are the examples for types of numbers? How to represent the floating point numbers? What are the standard format we have to use for representing floating point numbers? Single precision format and a double precision format. These are the points that we have to discuss in this video. Generally, there are two types of numbers. First one is fixed point number and the second one is floating point number. In the case of fixed point number, the position of the decimal or binary point is fixed. The decimal or binary point is always available after the decimal number or binary number. Now, these are the examples for fixed point number. The first number is a decimal number. In that case, the decimal point is available after the number 215. Next, the second one is a binary number. In that case, the binary point is always available after 1010. Next one, the third one is a decimal number because it contains the digits 0 to 9. In that case, the decimal point is always there after 3485. So, in the case of fixed point number, the decimal or binary point is always fixed. It is available after the decimal number or binary number. So, see these three examples. The decimal or binary point is available after the decimal or binary number. In the first example, the decimal point is available after 215. In the second example, the binary point is available after 1010. In the third example, the decimal point is available after 3485. So, the position of the decimal or binary point is always fixed. That number can be called as fixed point number. Now, whereas in the case of floating point number, the position of decimal or binary point is always fluctuating or floating. Okay, it is not fixed. The decimal or binary point is not always fixed in the case of floating point number. It is always fluctuating or floating. How it is fluctuating? See the first example one. This is a decimal number. It contains the digits 1 to between 1 to 9. So here plus 1.2345. Okay, the decimal point is available after 1. Next one, in this example 12.345. The decimal point is available after 12. Next, in this one, the decimal point is available after 123. In this example, the decimal point is available after 1234. So here, in the first example, the decimal point is there after 1. In the second one, the decimal point is available after 12. In the third one, the decimal point is available after 123. In the fourth one, the decimal point is available after 1234. So here, the position of the decimal point is fluctuating from left to right. Okay. Now, consider the second example. Now I am taking a negative binary number minus 1.01011. Okay, here the decimal point, the binary point is available after 1. Next, in the second one, the binary point is available after 10. In the third one, the binary point is available after 101. In the fourth one, the binary point is available after 1010. In the fifth one, the binary point is available after 10101. Okay, here the binary point is not fixed. The binary point is always fluctuating from left to right. Here in this case, the decimal point is always fluctuating from left to right. Okay, so here the decimal or binary point is always fluctuating from left to right or right to left. That type of number can be called as floating point number. Now, what is the difference between fixed point number and floating point number? In the case of fixed point number, the position of decimal or binary point is always fixed. It is available after the decimal or binary number. Whereas in the case of floating point number, the position of the decimal point is not fixed. It is always fluctuating from left to right and right to left. Okay. The general examples for floating point numbers are 3.14, 6.5, minus 125.5, 0.1101, minus 10101.101. These are the examples for floating point numbers. Now, what is floating point representation? The way of representing a floating point number internally in a computer can be called as floating point representation. Once again I am telling, the way of representing a floating point number internally in a given computer can be called as floating point representation. The general representation used for representing floating point numbers is plus or minus m into r power plus or minus e, where m corresponds to mantissa or significant. It is either a positive value or a negative value. R corresponds to base or a radix. Base may be 2 or a 10. Suppose base value is 2, it can be called as a binary floating point number. Base value 10 that can be called as decimal floating point number. Next, E corresponds to exponent. E contains either a positive value or a negative value. This is the representation we have to use for representing floating point numbers. Here, the mantissa is a signed fixed point number. It may contain either a fraction value or it may contain an integer number. So before mantissa, we have to use either positive sign or a negative sign. Suppose positive sign is there before mantissa, it can represent positive number. Suppose negative sign is there before mantissa, it represents negative number. Okay, based on the sign before the mantissa, we can say that whether it is a positive number or a negative number. So, mantissa always contains either a fraction value or an integer value. Next one. Here, xe corresponds to exponent. Exponent specifies the position of decimal or a binary point. Exponent also contains either a positive sign or a negative sign. Before the exponent, negative sign is there that represents numbers that are very small numbers. Numbers that are very small if the sign is negative before the exponent. Suppose before the exponent positive sign is there that represents numbers that are very big. Okay, so based on the sign before the exponent, we can say that whether it is a large number or it is a small number. Negative sign before the exponent always represents numbers that are very small. Positive sign before exponent represents numbers that are very big. Now, the decimal point or a binary point is moving from right to left. It represents a positive sign exponent. Okay. We have to move the decimal or a binary point from left to right. It represents a negative exponent. How it is a positive, how it is a negative, we can see these examples. Plus 1000.110. Now the decimal point, the binary point is there after 1000. Okay, now we have to move the binary point 4 places towards left. So then it becomes plus 0.1000110. How many places the binary point can be moved from towards left? 4 places. So that we have to multiply with 2 power plus 4. Okay, we have to move the binary point 4 places from the current position to towards left, so that after placing the decimal point towards left 4 places, the resultant number is plus 0.1000110 into 2 power plus 4. Next, now I am taking another example, minus 101011. Okay, here the binary point is there after the given number 1010.11. Now we have to move the binary point towards left. 6 places we have to shift towards left. So then it becomes minus 0.101011 into 2 power plus 6. How many places we want to shift? Whether it is a binary number or it is a decimal number. So in the power, that number we have to place. Okay, we have to move towards left the exponent is always a positive number. We have to move towards right. The exponent is always a negative number. Now we can see the third example, 1.2345. We have to move the decimal point towards right 4 places, so that this decimal point is there here. So then we get 12,345 into 10 power minus 4. We have to move decimal point towards right 4 places. So that it is a decimal number, we have to use the radix. We have to move the decimal point towards right, so that we have to use negative exponent. How many decimal places we have to move? 4. So that we have to multiply with 10 power minus 4. Next, we can see the fourth example, 215.37. We have to move the decimal point towards left 3 places. So after moving the decimal point 3 places towards left, we get 0.21537. This is a decimal number. We have to use the radix 10. How many decimal places we have to move towards left? 3. So that we have to use plus 3. Okay. Next one. 128.75. So this is a decimal number. The decimal point is there after 128. We have to move decimal point towards right only 1 place. So here this decimal point is moved to this place. Then what we are getting? 1287.5. Here this is a decimal number, so that we have to use radix is a 10. How many places we have to move? 1 towards right, so that we have to use negative number, minus 1. Okay, when we are moving the decimal point or a binary point towards left, then it represents a positive exponent. When we are moving the decimal point towards right, it represents a negative exponent. Okay, if it is a decimal number, we have to use the radix 10. If it is a binary number, we have to use the radix. Okay, in the exponent place, how many positions we have to move? That number can be placed at exponent. Okay, the decimal or a binary point is moved towards right. It represents a negative exponent. The decimal point moved towards left, it represents a positive exponent. Now, in this example, exponent value is plus 4, radix value is 2, and mantissa is only this one, 1000110. Next, in the second example, exponent value is 6, radix value is 2, and mantissa value is 101011. Okay, in this case, mantissa is a positive number. In this case, mantissa is a negative number. In this case, exponent is a positive number. In this case, exponent is a positive number. In the third example, so minus 4 is the exponent value. It represents a negative number. Radix value is 10 and the mantissa value is 12,345. It is an integer number. Here mantissa is a fraction number. Here mantissa is a integer number. So that mantissa contains a fraction or a integer value. Next, in this case, 3 is the exponent value. It is a positive number. 10 is the radix and the mantissa is a fraction number, that is 21537. Next, in this example, minus 1 is the exponent value. it represents a negative value. Base or radix value is 10. Next, we can go for normalization. How can you say that a floating point number is said to be normalized? A floating point number is said to be normalized if the integer part of its mantissa should be 1 and the fractional part of mantissa should be anything. Then we can say that floating point number is said to be normalized. Now we can see the example. We are taking a decimal floating point number 13.25. Here the integer part is 13 and the fractional part is 0.25. That can be converted into equivalent binary form, that is 1101.01. So 13 binary form is 1101. 0.25 binary form is 0.01. This is a binary floating point number. It is not normalized because in this case the integer part contains 1101, fractional part contains only 0.01. According to the definition of normalization, integer part contains only a single one and the fractional part contains anything, so that we have to move the decimal point towards the left 3 positions. So then we are getting 1.10101 into 2 power plus 3. We have to move the decimal point towards left, so that we have to get the positive exponent value. How many positions we have to move the binary point? 3 positions. So that we have to get plus 3. Here this is a binary number, so that we have to use the radix. Now check this one. In this one, the integer part of mantissa contains only a single one and the fractional part of mantissa contains anything. Hence, we can say that it is a normalized binary floating point number for the given decimal floating point number 13.25. Okay, in this way we have to convert the given decimal floating point number into equivalent binary floating point number in normalized form. Integer part of the mantissa should be 1 and the fractional part of mantissa should be anything. This is, hence we can say that a floating point number is said to be normalized. Now we are considering another examples. Suppose we are taking only a decimal number 385. Okay, what is the MSB bit is there? 3. 3 is a non-zero number. If the MSB bit value is a non-zero number, hence we can say that that decimal number is said to be normalized. Here the MSB bit value is 3. 3 is a non-zero value, hence we can say that it is a normalized decimal number. Next, second example, 0385. Okay, here the MSB bit value is 0. So if the MSB bit value is 0, we can say that it is not a normalized decimal number. Next, third one is 1.285. It is a decimal number. Okay, so the integer part of the mantissa should be 1 and the fractional part contains anything. So that we can say that it is a normalized decimal floating point number. Next one, fourth one, 0.235. Okay, so here the integer part of the mantissa is 0. Hence, we can say that it is not a normalized decimal floating point number. Okay, only decimal number we are taking. At that time, we are considering only MSB bit. If the MSB bit value is 0, we can say that it is not normalized. If the MSB bit value is not zero, non-zero value, hence we can say that it is a normalized decimal number. Here the MSB bit value is 3, hence we can say that it is normalized. Here the MSB bit value is 0, we can say that it is not normalized. Suppose we are taking a decimal floating point number, integer part contains only 1. Integer part of the mantissa should be 1. We can say that it is a normalized decimal floating point number. Here integer part of mantissa should be 0, so that we can say that it is not a normalized decimal floating point number. So this is the definition and examples for normalization. Now we can go for what are the standards we have to use for representing floating point numbers. To represent floating point numbers, an organization called as IEEE, Institute of Electrical and Electronics, proposed a standard 754 for representing floating point numbers. So IEEE 754 standard contains two types of formats for representing floating point numbers. First one is single precision format. It contains 32 bits. Second one is double precision format. It contains 64 bits. Single precision format. It contains 32 bits. 32 bits can be divided into 3 fields. The first field can be called as mantissa. 23 bits are allocated for mantissa, starting with 0, ending with 22. Next field can be called as biased exponent. That can be denoted by capital E dash. Capital E dash is equal to E plus bias. So 8 bits are allocated for biased exponent, starting with 23 and ending with 30, where small e can be called as exponent, and bias is nothing but the formula for bias is 2 power n minus 1 minus 1, where n is nothing but number of bits allocated for biased exponent, that is 8 bits are allocated. We have to substitute 8 in the place of n. So then we are getting 127. Bias value in the case of single precision format is 127. So biased exponent can be denoted by E dash. E dash is equal to E plus bias. E is nothing but true exponent and bias value is 127. And the last field can be called as sign bit field, that can be denoted by S. Only one bit is allocated for S. If S value is equal to 0, it represents a positive floating point number. If S value is equal to 1, it represents a negative floating point number. So this is the description about single precision format. Now we can go for double precision format. So double precision format contains 64 bits, starting with 0 and ending with 63. So 64 bits can be divided into 3 fields. The first field can be called as mantissa. 52 bits are allocated for mantissa, So starting with 0 and ending with 51. Next field can be called as biased exponent, that is E dash. Only 11 bits are allocated for biased exponent. The biased exponent E dash is equal to E plus bias. So where E is nothing but true exponent value and the bias value is equal to 2 power n minus 1, where n is equal to number of bits allocated for biased exponent. Substitute 11 in the place of n, then we are getting 1023. Bias value in the case of double precision format is 1023. Next field can be called as sign bit field. Only one bit is allocated for a sign bit. So if S value is equal to 0, it represents a positive floating point number. If S value is equal to 1, it represents a negative floating point number. So this is the single precision format and the double precision format. So 7 example problems are discussed on single precision and double precision format. Please refer the previous videos. Okay, I hope all of you understanding this video. If you really understanding this video, please click on the like button and share this video to your friends and classmates. If you have any doubts, please put your doubts in the comment section. I will try to clarify your doubts. For better understanding, please refer the previous videos on these two examples. These are very important in the case of GATE examination. If you really like this video, please subscribe my YouTube channel, Divvela Srinivasa. After subscribing my YouTube channel, click on the bell icon to get the future updates in my YouTube channel. Thank you one and all for watching this video.